Frank's talk really got me excited. I feel like I should pull a deck out from a workshop I was involved in back 6 years ago for the Academy of Sciences and Medicine. It was on a committee they put together that was writing some white papers related to sustainable agriculture, and different scientists from around the U.S. were brought in with very specific topics, and I was about animal agriculture related to genetics, and that was probably one of the most two interesting days. It was a real eye-opener for me because that committee was made up of members of both the scientific agriculture community, but also the community that maybe views things a little different than a lot of us in agriculture as it relates to agriculture production. And to watch the battles that went on between science and myth was extremely intriguing and really gets you fired up. So we're going to change gears a little bit. We're going to talk about technology and biotechnology, genetics and reproduction specifically, and where the industry is at the present, and what we do at Transova, and our thoughts and views as it relates to technology, and why we continue to look at new technologies and developing those technologies with the traditional advanced reproductive tools that we use. A lot of my talk has been set up great. Dr. Walton did a wonderful job this morning setting this up. Frank hit some great points too. We've had discussions, so we don't have to say a lot about there, but Transova and all of us that work there, and why I went back to graduate school and stuff, passionate about agriculture, but passionate about what we can contribute and what we can do over the next 20, 30, 40, 50 years and our children in this area of food animal production, and extremely proud of where we've come the last 100. Especially in the U.S. and North America, it's really mind-blowing when you think about it, what production is actually done and accomplished. So a quick outline review, and I'll try to keep moving through as we get moving towards noon, and we have quite a bit of things yet to happen in this session. We're going to review genomics and genetic gain, these tools, and how genetics have made this movement. We'll look at the assisted reproductive toolbox that we use. We'll talk a little bit specifically about in vitro fertilization applications, or in vitro production of embryos and livestock, and how that fits. We'll talk about cloning and beef and dairy and the cloning applications. Dr. Walton and myself and Transova have been very involved historically in this area, an area that we very much believe in and where it contributes. And you'll learn about how these combine in the hierarchy of genetics and how these things keep moving genetic advancements that make us more efficient and higher quality products. Biomedical applications as it relates to primarily in bovine models that have been done, and a couple models that Transova is involved with in that. But then we need to talk a little bit about genetically modified cattle, and Dr. Walton talked about it today where the technology sits, but gene editing and the role that plays in the future of production. And I'll kind of wrap that up there. So what is ART? Why do we use ART? Well, if we go back, and easily the greatest development in cattle agriculture, in advancement of genetics and in our production systems was the beginning of artificial insemination in the 1950s. That was followed very closely with the ability to freeze bovine semen in the late 50s and early 60s. And that changed genetic improvement in beef and dairy cattle in the U.S. and now and around the world. The early embryo transfer work, the ability to take a female now that has one calf a year, maybe has 6 or 7 in her lifetime, super ovulate her to stimulate to ovulate greater than a single egg and get many, artificially inseminate her, let her be an incubator for 7 days, flush the embryos out, transfer those embryos into recipient females or surrogate mothers, if you think about it, how they would talk about it in humans. All began and it started happening from a research perspective in the 70s, and by the late 70s was being commercialized. During that time in the 70s, Dr. Wilmot's group over in Edinburgh showed research and was able to freeze the bovine embryo, and that's back in like about 73 or 75. That also advances technology to another level. The ability to cryopreserve an embryo and be able to then put it in at a given point in time and from a management scheme is huge and is massive in what we do today. IVF in cattle started in the early 1990s. It's been a long haul, but over about a decade ago, some of the kinks in this technology were worked out. And this technology has exploded, not just in North America. other parts of the world, like in South America, at a much faster rate, and is growing quite rapidly in the U.S., complementing these embryo transfer, become part of these traditional in vivo ET programs. The cloning that started in the late 90s in genetic preservation, being able to take a tissue sample, create a cell line as an insurance package, bank it away, and if needed, make an actual identical clone or a clone of that genetic donor. And then in the early to mid 2000s, the advancements with our ability to sort sex semen, and we'll talk a little bit about that, which coupled with these three technologies has become extremely powerful. But this is all about a simple equation. As a quantitative geneticist, I have to throw an equation up, but genetic gain, how we make genetic improvement. Well, there's genetic variation segregating in a population, and that's what we're selecting on. We're selecting a certain portion of that population to be the parents for the next generation. So what are those animals that are the extreme individuals for whatever it is the selection criteria it is we select? This is what's changed in the last 5-6 years, is the accuracy of selection. And what's changed the accuracy of selection is the advent of genomics, the bovine sequence. I was part of a team at Clay Center and with the USDA at Beltsville and the University of Maryland, and scientists at the University of Alberta. We built the first bovine SNP chip, which was a 50K chip. That changed this ability of accuracy selection in extremely young animals, which allows us to change generation interval and move genetic gain faster. And you couple that with the technologies that Transova uses, where we can get lots of progeny out of a single female over the course of a year, mated to a bull or multiple bulls, and suddenly you're moving this at a much accelerated rate, and that's exactly what we'll see, and we'll have some examples of that. So this is what the toolbox, the reproductive toolbox looks like. This is Transova's toolbox and how it looks right now and in everything that we do. I mentioned embryo transfer, in vitro fertilization. The ability to sort semen, X sperm and Y sperm, actually run them through a sorter and freeze that, but even more important, the ability to take any straw semen on any bull, and a conventional straw or even an ampule bull, way back into the 70s, run it through the sorter, and then use that in vitro fertilization for desired sex has really changed the industry and is a big part of our IVF program. Recipient solutions, you have to have places to go with these embryos. And that is something that as we look to the future and we see some of the changes happening with beef dairy, where we're taking genetically inferior animals in the dairy herd, but they have to become pregnant and they're giving milk, but they're not going to produce the next generation. There's opportunities to put beef embryos into those, and we're seeing some beef dairy cross programs. This is a change. This is a change in cow inventory, a need that's there, a feeding capacity that we have way more than what we have available right now in the U.S., so we're going to see some different programs evolve and things happen in that regard. Transova also does some things with genetic resources and related to the Jersey dairy breeded cattle, and using these technologies to push genetic improvement. And of course, we are extremely passionate, and we own the Biogen as a division of Transova, the cloning company, and continue to work in the area of cattle cloning. Also do a lot of cloning in swine, horses, and some in sheep and goats. And an area of the future, and Mark was talking some about this as it relates to, in the words of his colleague Scott Ferrykrug likes to say, precision animal breeding. Precision, and we're doing what we've done as animal breeders. We've selected for these animals that are segregating a certain form of a gene, like let's say it's double muscling. But now we have the technology. What if we took that gene allele and we took a Wagyu and we went in there and went to that myostat locus and put that Piedmontese allele in there? We now have done what would take 7 or 8 generations of crossing the two breeds together and then crossing to the breed that you want it to be pure all in one shot. And that's the power of this technology and where it's going. And we've seen it happen in crops and where we need to get to. It's going to be all these tools and not any given one of them that does this. We were asked to kind of give a little bit of a look at what we look like. We're a technology company that takes technology all over the U.S. We're in Sioux Center, Iowa. We have IVF labs in 3 locations. We have donor facilities across 5 or 6 locations. The blue dots represent day centers where we actually work with vets and other practitioners and send teams in to do the OPU, which is the ovum pickups in the IVF process. And we continue to grow that and work diligently. We have recip operations in Oklahoma, Iowa, and Missouri for our beef producers, and a large calf operation dairy calf operation in Sioux Center, Iowa. It's about happy donors and happy recipients, just like humans. When animal husbandry is important, proper environments, cows being maintained and managed in the right environment, and having high comfort levels make more embryos, and recipient females tend to get pregnant. The facilities and handling and animal welfare and being able to be efficient and make tens of thousands of embryos every year with these different technologies, and then having wonderful sets of people working in our various semen, IVF, and cloning and R&D labs is a big key. It's all about people make it all happen. Part of what is driven in the genomics really drove this is our live calf operations in dairy. So as soon as the genomics became part of the genetic evaluation in dairy with a genomic enhanced PTA, you now, the day a calf is born, have the ability to take a DNA sample. The genomics are submitted. The calf is the genomic genotypes are ran. The genotypes are then sent to the national evaluation. This starts explaining part of the genetic contribution of that calf. So that's enhancing the accuracy. It's kind of like that animal at like 30 days of age suddenly has progeny that you've been measuring phenotypes on. So example, in Holstein, the progeny equivalence for that animal, bull or female, when it's born, for its milk genetic merit number is somewhere between 30 and 40 some females, daughters of that cow or bull, with milk production records. That is powerful. So that is what it does. We now have enough information then to select at an extremely young age and now we start working on younger animals, and genetic gain accelerates at an extremely fast pace. In vitro fertilization, this is a technology that Transova has been involved with since 1992 at a commercial level in the industry, and continues to work in the R&D space in this area. But it gives us some opportunities and things we can't do with traditional in vivo ET. We have the ability to use when pregnant females, so we can do a bred heifer or cow up to 100, 120 days of gestation. So she's gestating a calf, staying in a normal production cycle, and she's making calves in the process. Our ability to do it in very young heifers. We push the envelope all the way down to juvenile heifers at 6 months of age. We start most of them probably on the clients that want to push the envelope around 7 or 8 months. It really puts some when the first round of those started hitting, the filters that some of the breed associations use, these females were suddenly registering calves and they weren't old enough to have one themselves. And that's been an adjustment that the industry's had to go to as these producers and us have pushed genetic gain. It's the best place to use a sex semen from a standpoint of what we can do with reverse sort and availability of almost any bull. We produce lots of progeny out of a single cow, and with both ET and IVF, but this is a technology that's grown a lot. Very science-driven. It's very technical. You're taking the incubator out of the cow and you're controlling the fertilization out of the cow. So you've got a lot of things that can go wrong, and a lot of systems in place, and a lot of really talented people, young scientists and old scientists that handle that day to day. So how does it work? Real quickly, we do what's called a transvaginal ovum pickup, an OPU. This is a ultrasound probe. There's the ultrasound is on the end of this probe. This is a long needle that's hooked to a vacuum. You manipulate the ovary to the side of the vaginal wall, the needle, and you just aspirate those ovum right off of that ovary. We can do this every other week on a cow, so you start averaging 5 embryos every other week produced out of a cow, and we can go quite a few weeks on cows over and over on these high-producing cows, allowing producers to make a lot of progeny, a lot of embryos extremely quick. And with genetic gain, it's about numbers. If you make 1,000 matings, if you could do that out of a superior bull and a superior cow, your probability of getting, you're going to get a bell curve distribution, and getting those elite outliers that are the elite ones for the next generation increases that much. So it's about hit. Not every animal out of a superior cow and a superior bull is even going to equal the average of that. A great 2/3 of them will be around the mean of those two parents, but you're also going to have some animals that don't. Just like any full sibs and siblings, my brother's 6'2" and probably weighs 20-some pounds less than I do. We're full sibs, but quite different in the genetics we inherited from growth from our parents. And that's something to always to think about and consider. And Mendelian sampling is a very powerful tool and keeps us as geneticists from totally screwing everything up. So, sex semen, I talked a little bit about the ability to use flow cytometers and dye and sort the X and Y bearing sperm, and reverse sorted semen, as we call it, where we can take a straw of semen, has been a huge part of probably 50% of all the OPU events that we do at Transova. We're reverse sorting semen daily for those specific in vitro fertilizations that we do. We have the ability on high-producing cows to split oocytes and fertilize the two different bulls. It gives you a lot of freedom and a lot of opportunities to do some very specific things for the producers. So I mentioned a little and probably got a little ahead of myself, but this really changed dairy, and it's having a huge impact in beef. But what it allowed us to do was we can screen dairy animals, females especially on the female side, and get this genomic enhanced genetic merit number. It allows us to get information on these young females, like I said, with a lot of progeny equivalents, and collect oocytes out of those females and fertilize an IVF in the IVF process. A lot of sex semen gets used in this system, and this is an example of a female. Those are 3 OPU events. There's 20 heifer calves in that, born within about 30 days of each other. I think to four different bulls in that. But just an example of the power of the technology. The dairy industry is going 100 miles an hour with making genetic progress. And if you look at genetic trends for milk or the indexes that are put in net merit in dollars, and what they were doing like this, you can go back and look at the same charts from the 90s as we started having additional genetically improved crops at the market, and the slope of that line has improved dramatically. And so we were making great progress. If you think of what happened in the previous 50 years with artificial insemination, progeny test programs where these bulls were 5, 6, 7 years old when they were proven, getting used a lot, you've now totally turned that upside down. And so the females are extremely young, and these young bulls are being used because of this information, turning the generations over faster, and it's working extremely well. And we're starting to see the impact in the beef industry slowly with that, and we'll continue to grow the use of genomics coupled to ART. So cloning. Cloning has been something, as we looked at that first slide, I look at it as the very top of the pyramid. Cloning is something that is used to make copies of those very special animals, or those animals that died at an extremely young age. We make quite a few bovine clones a year for our clients. The dairy industry, it's been on the female side multiple copies of these really elite animals. These females that are extremely high, that they've wanted to make lots and lots of progeny, or the genetic donor herself, her reproductive cycle is starting to fade off, and she just doesn't make, she can't get pregnant, she's not making embryos. It becomes a great technology to make a genetic copy of her, and to continue that she's able to have that kind of influence in the industry. A great success story, this is a Holstein bull. This is actually the clone himself. A bull that was a lunger as a baby calf. And that means that he had a disease related to a virus, which is very common in these young dairy calves. His lungs never overcame it very well. He was not very thrifty. His growth curve was not very good. They had a hard time getting semen out of him. They got a little bit. the genomics then hit, and his numbers were really, really good. Well, so they had gotten some cows bred to him and had some daughters that were coming into production, so the AI company decided that they would make a clone. The clone was born, he was a normal, healthy bull, normal semen production. During that time, the handful of daughters proved themselves out to be extremely good producers, and this clone, this genetic copy, estimated to have sold over 100,000 units in the U.S. and internationally. This bull would not have had the impact and allowed his superior genetics for the traits that he was so good for to impact the breed and would have been lost uncaptured genetics. Nothing to do with his genetics. A typical deal. Not every animal that's born is able to stay healthy, just like humans get sick in that. And a great example where cloning technology allowed genetic resources to be captured. Beef producers, much the same way and much the same thought process. There's been a terminal sire that we've made many, many copies of over the years. When they hit a certain age, their semen production falls off. We're really happy that he gets used as a terminal sire all the time. But cloning is allowed. The bull's been gone for quite a while. Has allowed the owners to continue to make copies and freeze semen on this sire. Young outliers that die at a young age. A lot of people use the technology as an insurance package. They put away either a tissue or have a genetic preservation cell line put away, with the opportunity that if something happens to that animal, they can still make a copy of it and harvest those genetics in moving their program forward. A good example of where a breed of cattle had a couple major defects show up back in 2008. The saturation amongst the breed was pretty large. A group of breeders that owned a cow that had been a lot of daughters and a lot of sons born out of. The problem was a lot of those progeny or carriers got together and made copies of that very, very old cow, going back and using then the new young bulls of the day that were clean for the defects and not losing a great proportion of her contribution to the industry at that time. And then there are these examples of these extreme outliers that are way out there on the genetic curve and improving themselves, and they need more progeny, both in males and females, in cloning opportunities, making that possible for our clients. What about product safety? Well, the FDA cloning at risk assessment in 2008, and I was actually at Clay Center when they did a large part of the pig part of that. But food from clones of cattle is safe, and the food system no different than conventionally produced beef. Transova and Biogen were very involved and had a supply chain management program. Ran that program for 8 years, a lot of dollars and a lot of recording and everything. Some competitors wouldn't participate, and in 5 years we never once had anybody asked to access that information in that. And so it was evaluated, and from outside of even the companies involved recommended that we drop that. So as far as concerns and everything, over that 5-year period, it was never once accessed in that regard, and that's something, is a good positive point. So applications of biotechnology, and this is something Transova, we've been involved in biotechnology. We think biotechnology, genetically enhanced, and we would think about it. The things we learn when we work with genetically modified cattle in the pharmaceutical world impact things we do in the commercial production side. Things we learn about our culture systems, things we learn about the technology have positive impacts on our ability to do things with IVF and other technologies and that. Also, we really believe at some point in time, if we're going to feed the world, these technologies, and especially like gene editing, are going to have a huge impact. And we've got to get over that hurdle in making that happen on the livestock agriculture side. Transova has been involved in an animal that they could make recombinant human albumin in the milk. Probably the biggest, most successful genetically modified cattle animal is the TC cow. And this is a really neat pharmaceutical production bioreactor. This is a cow that has had its immune system turned off, a lot of it turned off. So the genes for that have been turned off. And then they inserted in these cell lines a human artificial chromosome that codes for a large part of the human immune system, that your complement of your immune system that makes all those antibodies that recognize foreign things in your body and then produce antibodies to fight that. So this is going the TC cow. This animal then can be inoculated with things. The animal's body responds to that, and then they can do bleeds, and they're small bleeds. The animals aren't sacrificed, and you can do it over time. Purify those human antibodies out, and in some cases either make a polyclonal vaccine, or they start looking at specific targets that exist for whatever the endpoint is, and making monoclonals, finding those and then making monoclonal antibody lines. The opportunities with this in Sanford Applied Bio is the scientific partner. We're the animal husbandry side. We take the embryos, we do the gestating, we do all the delivery of the animals and rearing them up for them to then create on the human pharmaceutical. Powerful model. Another powerful model is the medical pig models that we work with a company called Exemplar. These are pigs that have had their genomes modified to express human diseases. So there's a cystic fibrosis pig, and at the University of Iowa, when that model was done and when we got it up into regular production, they said they learned more in a 2-year period about cystic fibrosis than they had the previous 25 about past with targets and improving medicines. The power of these models to be able to mirror they have a cardiovascular pig that's a high cholesterol pig. There's about 9 or 10 models right now, and these pigs are having, and will have, we believe, an impact on a human medical research. The mouse, which dominated from when you look from the 70s, 80s, and 90s, had been a great model to do these things in, but oftentimes the targets and the things that we learned using a genetically modified mouse, mimicking, looking at a phenotype with a human disease, then when we went and started looking at it in humans and stuff, it didn't match the evolution of time and the distance between the mouse and the human. We know pigs are much closer when we look at mammals, and the ability with xenotransplantation, organ transplant, and using pigs as medical models holds a great potential, and is still an animal in a size that can be managed in a research setting. So we've talked about this a lot. I keep alluding to it. All the other speakers keep alluding to it. We've had this happen in plants, and if we look across many parts of the world in the U.S., a huge proportion of the crops that we raise are, one, traditionally genetically selected, selection lines going on, and then we've been able to go in and tailor these and create things. And we look at BT, all the BT crops that exist. We look at some of the new drought stress varieties coming out. Genetic selection and being able to enhance the genome to increase productivity and doing it in a way that's acceptable and safe is huge. So we got to get to this in livestock. I mean, I passionately believe this. Dr. Walton believes this. Many of us do. Many of us think that we would be even farther down the road, and I'd be showing you that toolbox with animals, production animals. It won't replace everything else we do, just like it's not done, like it hasn't happened in crops. It just is going to enhance and give us the ability to do things a lot better. These are all examples of, a couple of these are actually projects that were done. And these are a lot of them sitting on the shelf. Lack of funding, lack of things. It could be huge impact in humans. This one Dr. Walden mentioned today, and this one gets even me excited, being a kid that grew up with horned Herefords and trying to make them pull, just doing traditional genetic selection and spending generation after generation trying to create homozygotes of quality. The ability to go in there and do this in a boom, one generation, one animal, and begin to do that, the power of that. And that's a nice example, relates to something everybody would like to see less of, and from an animal handling, welfare, quality, all those kind of standpoints, but it's just one of many of the natural segregating things that exist in these animals that we could move from breed to breed, and move around. And as we precision animal breeding, I like to say. And it all has to start with this one. And Dr. Stodish will be talking a couple times over the next couple days, but we have to get this. This model, my marker died, which is good, is reached every hurdle, and is science and everything to that. We have to get it over over to the next step and get to an actual production and acceptance and get let the science speak for itself and perception and get over the hang-ups with this model. It's the first step and the start that allows a lot of these other things to happen for the betterment of agriculture and feeding the world. So something on the near future and combining technologies that exist in that. Biopsying embryos has been something that's been done for many, many years. Oftentimes it has a fairly large impact on pregnancy rates. We've been working really, really hard over the last year biopsy techniques and have been able to develop techniques with our cloning teams where we can biopsy embryos, freeze the embryos, both in vivo and IVF, get the genomics, the genotyping with the genomics done and submitted to the genetic evaluations, get the rankings of the animals back based on their genomically enhanced genetic merit numbers, make selection of which embryos need to be transferred, and we just finished an R&D experiment with both in vivo and IVF frozens where we had very, very acceptable preg rates. In fact, really good. So we're really excited we're talking about young females doing OPUs, and now we're talking about making selection and backing it up, even changing that generation interval even faster, the ones we put in, allowing the producers to put in more of what they want and move things faster as far as the calves that they're gestating and having to raise. A lot of fun opportunities there. It's the value of our technology to consumers. You start looking at all the different areas as it relates to animal health, animal longevity, product quality. We can, the diminished environmental footprint is so great to listen to Frank say that it's that intensified increased amounts of energy and the efficiencies when you compare the numbers in that. And going back, we've heard it quoted a couple times. When we look at the history of milk production in the U.S., the 16 million less cows, we only have 9 million dairy cows in the U.S. We're 16 million less, 9 million now, producing 60% more milk, or anywhere from 2 to 4.5 times more milk than we did with a population much bigger, and we export a large portion, and that's pretty incredible. That's an example of all of those pieces of management, reproduction, and genetic selection. And all those pieces contribute, and we'll see all the species. We've seen it happen in poultry, we've seen it happen in swine, we're seeing it happen in dairy. Beef will be a little bit different model because of the large expanses of land that it takes, and we can actually utilize that land, grazing some of this rough forage and that stuff. But this process that's gone on and this intensifying of using tools and management practices to enhance production and production efficiencies. So these are a couple of quotes that I really enjoy and like to use as we're wrapping this up. But which technology does this quote, the first quote, come from? It's unknown what long-term health consequences may unfold. The studies are not adequate. This is like every time a new technology hits. Furthermore, this will likely not be available or cost-effective for small farmers. It will decrease product acceptance, consumption, and will be catastrophic to small farming operations. And it's not artificial insemination. That's the first one, and it's definitely not cloning. This is 1924, the pasteurized milk ordinance. Saved probably millions of lives across the world. But that is a technology that is so important and that's how it was viewed when it first hit. Once again, science, education, being advocates of everything that we do and understand, and helping people understand that technology is good. When they don't understand is when they get nervous. But as scientists, I have to remind myself, it is so fun to get so tied up into science and explain the science to people, and you can lose them. And so keeping it simple is extremely important. So this next one, we're talking about possibly human-animal hybrids, monstrous babies, and reproductive engineering. Children conceived this way will have no soul. And it's not cloning, because that doesn't go on with humans. But this one is, in my lifetime, that was in 1978 when baby Louise Brown was born, first IVF baby. And there's been well over 2 million, probably more like 3 million now. This is a quote from a few years ago. But just thinking about technology and us in agriculture and as we face these different things.